One of the most remarkable formulas in all of mathematics is Euler's formula. Euler's formula says that e to the I theta is equal to cos theta plus I sine theta, which has the incidental consequence that e to the I pi is equal to -1, which is one of the more stunning results in mathematics. Now, in addition to being a remarkable mathematical result, this expression is what makes it very useful to use exponential notation in algebra for physics and engineering and many other subjects. It's a major reason why we use complex numbers in engineering, for example. Exponentials are basically much easier to manipulate than sines and cosines. Multiplying exponentials together is straightforward, it's just a matter of adding powers. Multiplying sines and cosines together, we can do it, but there's a whole lot of formulae in order to do that that we might have to remember, and that can get quite complicated. So let's just look at a few basic results that follow from Euler's formula. So here's Euler's formula again. X I theta, e to the I theta, where theta is some real number, is cos theta plus I sine theta. And note immediately, of course, from our understanding of powers, x of minus I theta is equivalent to x of I times minus theta inside the exponent here. And that means that x of minus I theta is cos of minus theta plus I sine of minus theta. Well, that is just cos of theta minus I sine theta, because cos of minus theta is equal to cos of theta. Sine of minus theta is equal to minus sine of theta. So the complex conjugate of e to the I theta, x of I theta, is x minus I theta, e to the minus I theta. Also, e to the I theta times e to the minus I theta, exponential of I theta times exponential of minus I theta, is exponential of I theta minus I theta, of course. We're just multiplying two exponents here. We add the powers. And of course, adding these two together gives us 0. And e to the power 0, or exponential of 0, is 1. So, if we look at this product here, x of I theta times x of minus I theta, we're going to be able to use this result to prove a very standard result in algebra of trigonometric functions, just as an example here. So we can write this one out as cos plus I sine theta. We can write this one out as cos theta minus I sine theta. So multiplying the two of these together, we get cos squared. We get I sine times cos theta. And we get I cos theta times sine theta from this pair here. And then we get I sine theta times minus I sine theta, which is I squared sine squared theta with a minus sign in front of it. And that, of course, we see we cancel out the middle terms here and here, is cos squared theta plus sine squared theta. So this proves that cos squared theta plus sine squared theta is equal to 1. This is just an illustration of using Euler's formula to get a useful result. We can prove it by other means, of course. We can prove it from Pythagoras' theorem. But this notation in Euler's formula gives us a very simple way of proving these kinds of formulas related to cosines and sines. Now, for any complex number a plus ib, we can trivially multiply top and bottom lines by modulus of g if we want to, which means that since we know the modulus of g is the square root of a squared plus b squared, we can write any complex number as its modulus times this term and this term here. But of course, we recognize those as cos theta and sine theta. If we look at our triangle here, that will remind us the sine theta is b over r, the cos theta is a over r, and the r is the square root of a squared plus b squared. So that means that any complex number can be written in the form the modulus of the number times e to the I theta, or exponential of I theta. And that's called the polar form of a complex number, and it's extremely useful. It means also that we can usefully start to think in what can be called a complex plane. So we can propose a mathematical plane. It's not a real physical plane, it's a mathematical plane with two axes at right angles to it. We conventionally plot the horizontal axis as the real axis and the vertical axis as the imaginary axis. Then any complex number we can imagine, which we can write in the form of a plus ib, we can plot it as a point on this plane. Kind of like adding vectors. These are not actual vectors, but it's like adding vectors. So we can go along this plane, this direction here, by an amount a. We can go up this direction here by an amount b. Those give us the coordinates on the complex plane of this point, which we have already convinced ourselves is mod g times exponential of I theta. And the length of this line is the modulus of g. And the theta on this diagram is precisely this angle in here. So it's like projecting components of a vector. It's exactly the same kind of algebra. We're talking about now this imaginary plane, and then we also have this additional result, which you would not get from just an ordinary vector projecting onto axes. You would get these terms, but you would not also have that result in ordinary real algebra. And of course, g is just the modulus g is just the square root of a squared plus b squared. Now, this kind of diagram, plotting a complex number on a plane like this, is sometimes called an Argand diagram. This modulus here and this theta, and they're used a lot in engineering and also other branches of science. Sometimes the theta here is called the argument of the complex number when it's written in this polar form. And sometimes people use this notation, theta is equal to the argument of g. Now, argument is used for many different purposes in mathematics, and this is just one of them. I will not myself probably use this notation very much, but you will come across that. In this polar representation of complex numbers, multiplication becomes very simple. So in our polar representation, we can write our number g, as we said, the modulus of g times e to the I theta, or exponential of I theta. To multiply two numbers, all we have to do now is multiply the moduluses, or the moduli, these numbers, and add the angles. So if we have another complex number h, which we can write as the modulus of h times exponential of I phi here, then g times h is modulus of g exponential of I theta times the modulus of h exponential of I phi, which is modulus of g times modulus of h, and exponential of I times theta plus phi. So multiplying those two numbers on the complex plane merely means we multiply the moduli and add the angles. One other topic that we will touch on, because we will come across it later, is a slightly odd topic called the roots of unity, and specifically what we call the nth roots of unity. So when we take this number here, exponential of 2 pi I over n, and n is typically an integer when we're working in this discussion, when we raise that to the nth power, we get unity. We get 1. So explicitly, here's exponential of 2 pi I over n raised to the nth power. We merely multiply the exponents. The n's cancel here, leaving us with exponential of 2 pi I, which is 1. Now, there are many different complex numbers that when we raise them to their nth power can give us 1. But this specific one is conventionally called the nth root of unity, and written in this notation here, where the n is a square root sign, but with this other number in front of it means that it's not a square root, it's an nth root. It's the number that when raised to the nth power gives us the number inside here. And what we're saying is that one way of writing the nth root of unity, or of 1, is exponential of 2 pi I over n. And that will come up later on in physics, especially of what are called periodic systems. Finally then, let's just end with a few useful algebraic results here and some formulas that we can deduce using the complex numbers. So there are many algebraic identities we can come up with that we can prove rather easily with the complex exponential form. So this one is very easy to prove using complex exponentials, that the complex conjugate of the product of two numbers is just the product of the complex conjugates. We could prove that other ways, but it's really easy to prove with the complex exponential notation. Similarly, it's very easy to prove that the complex conjugate of 1 over a product of two complex numbers is just 1 over the product of the complex conjugates. And the complex conjugate of a ratio is just the ratio of the complex conjugates. Again, very easy to prove using complex exponential form. And finally, just to mention the sine and cosine addition formulas, you may earlier in your career have learned a large number of these formulas. They can be proved with trigonometry, but sometimes it's a little tedious to do that. But it's very easy to prove these using complex notations. So all of these sum and difference formulas for angles and so on, we can deduce very simply. For example, if we take the exponential of 2I theta, then using Euler's formula, that's cos of 2 theta plus I times sine of 2 theta. But also it is exponential of I theta times exponential of I theta. And that means it is also cos theta plus I sine theta squared. I'm just multiplying this number by itself. Now, we can multiply this part out here. We get cos squared theta plus sine squared theta plus 2I sine theta cos theta when we multiply all of this out. So we can equate the real parts of both sides. So we can equate the real parts of this to the real parts of that, which is also just cos 2 theta. So therefore we get that cos 2 theta is cos squared theta minus sine squared theta. And if we equate the imaginary parts, that's I sine 2 theta here, is equal to 2I sine theta cos theta. In other words, sine 2 theta is equal to 2 sine theta cos theta. It's just an example of how we can work out all of these sine and cosine addition formulas.